Hey guys, it's week 7. This is a video for Gen Chem for learning the difference between global climate change and ozone depletion. So we're going to be talking about air pollution, water pollution, etc. Over the next 2 weeks. We're going to squeeze in what we can. And a lot of these conversations are going to come up where we'll talk about a particular substance and then whether or not it has an impact on global climate change, ozone depletion, or if it just has a human health impact, and that's something that we worry about. So today we're going to be looking at the basics of what ozone depletion and global climate change are, okay? So what I'm going to start with is this. So I would recommend that you go ahead and pause it really quick, and then in your notebook, copy down something similar to this, because we are going to be kind of jotting a couple things over here, not too much, so you don't need to leave yourself too much space. And then I'm going to be drawing something on here just so we have an idea of what we're kind of talking about. Okay, so pause the video if you need to, and then go ahead and set this up in your notebook so you can copy down some information. All right. So what we're going to be looking at first is ozone depletion, as we saw. So a lot of people have heard of ozone depletion before. And there is a very large misconception that ozone depletion and global climate change are either the same thing or are related. They are completely unrelated. There may be some, stepsisters, cousins, best friends, hairdressers type relationship between ozone depletion and climate change, meaning it's a stretch. But there really isn't anything that's directly related between the two. So that's a huge misconception about the two. A lot of people think they are the same thing or that they're related, but they are not. So ozone depletion says cause. All right. So the cause of ozone depletion, I'll write it on here and then I'll be showing you guys later. The cause of ozone depletion is chemicals reacting with ozone. And I'm going to put in parentheses O3 because that's what ozone is. Ozone is basically oxygen gas, O2, where you have two oxygens. Remember, oxygen is a Brinkelhoff. It's the O in Brinkelhoff. So it generally forms as O2. You add a third oxygen to it, and you end up with what's referred to as ozone. It's a weird structure. If you go on into AP or IB Chem, you'll learn a little bit more about the structure of it and why it might be designed that way. But the idea still stands as O3. So chemicals reacting with ozone, O3, chemicals reacting with ozone in the stratosphere and causes the ozone layer to deplete. That's a good way to put it, I suppose. As good as it can be. So this is when chemicals react with the actual ozone, the chemical. A lot of times people refer to ozone as like the layer, but we call it the ozone layer. So ozone itself is a chemical O3. So substances can react with that O3 and essentially kind of change it into O2 and also sometimes leave some other negative impacts in that particular place. But that is essentially what's happening. It's just chemicals that have gotten into the stratosphere that are reacting with the ozone in the stratosphere. So what chemicals, you ask? CFCs. CFCs, chlorofluorocarbons. All right. So chlorofluorocarbons indicates to us that chloro is the prefix for chlorine. Fluoro is the prefix for fluorine. So these are some sort of carbon compounds that contain chlorine and fluorine. And in fact, a lot of CFCs are literally just like CH3Cl or CH3F, meaning it would be a carbon, 3 hydrogens attached, and then just a fluorine. So a CFC really can just be as simple as a carbon compound that has one fluorine or one chlorine attached, or it could be a lot more complex. Now, a lot of these CFCs came from propellants, from hairspray and from spray paint and other things like that. Back in the 1980s and maybe 1990s, I don't think, but I'm pretty sure it was 70s and 80s primarily, when everyone really wanted the big hair. Those types of things became extremely popular. and the propellants they used were chlorofluorocarbons. And so what we're actually seeing is that those substances took about 20 years or so to get from the surface and then slowly dissipate up into the atmosphere, to the stratosphere. So what's happening right now, or when the ozone was being depleted at its worst, it was actually chemicals that were 10 to 15 years old, that had taken 10 to 15 years to really rise from the surface up to the stratosphere and react with that ozone. So what we're seeing now is that because we realized that that was a potential problem, CFCs were banned as propellants and banned in most cases. And so what we've seen from that is that the ozone really has made a huge impact, or we have seen a lot of the ozone reforming, because without those substances rising from the surface, less and less of them are rising up over time, and so we see less and less actually occurring. So the effect that that has is what it was doing is allowing ultraviolet light into the troposphere, but into the lower atmosphere. And hold on one second. Sorry, my cat came busting in, and so my roommates are in the kitchen talking, and it was kind of distracting me. So anyways, it allows ultraviolet light into the lower atmosphere, and so that was, since the ozone layer was actually occurring over Antarctica, that happened to be, and that was really just related to global air circulation patterns. A lot of those chemicals that were rising up from the surface, you are not going back out yet. You can wait. She came busting in, and then now she wants to go out. Any of you who have cats understand exactly what I'm referring to. Anyways, so the ozone layer, because of global circulation patterns, all of those CFCs were making their way down to the South Pole, and that's where they were collecting and causing that erosion of the ozone layer in that particular area. The entirety of the ozone layer was not necessarily eroding, it was really just that hole that was opening in that particular place, allowing a lot of that ultraviolet light into Antarctica, which is predominantly an ice continent. I mean, it's a land continent with mountains and things, but it's covered in ice. And so it was allowing that in there, and that was causing the... She's chasing something under the bed. It's really distracting. All right. I'm going to break this into a two-part video, obviously. But it was basically going in, causing some melting of the ice cap, also causing severe damage to organisms that live down there. With the ozone depleting, any sort of organisms, such as whales or things like that, that were found underneath that particular location, we're getting extreme sunburns, because without the ozone is really there to protect us from the sun. Not that we put it there, but the fact that it's there has allowed those of us who have sensitive skins, such as humans who have our skin exposed, allows us to survive. Without the ozone layer, we would just fry instantly and just all have skin cancer, even if we survive the initial impact of the frying. So it's kind of important. So the reason I drew the drawing there is just to kind of remind us that what was really happening with the ozone layer. Again, it was at the South Pole, and so we really were just kind of opening up that portion of the atmosphere, and that was allowing these waves of energy, which would normally be blocked by the ozone, to not be blocked. So if that were to have eroded much larger, we would have seen a massive impact on human health, a massive impact on animal, plant life, etc. Because even plants, we think they like being in the sun, but they like being in the sun under the ozone layer. Okay? If you expose a plant to direct ultraviolet light, it ain't good. Case in point, coronavirus that we're dealing with right now. It is a substance that obviously, or it's not a substance, it's a thing. It's not an organism. It's not alive, so it's weird. But obviously it's causing all this havoc, killed by ultraviolet light. So obviously, concentrated ultraviolet light is something that is extremely impactful. Now, don't take me saying that as a healthcare professional or anything, okay? Yes, it is proven to be killed on surfaces with ultraviolet light, not in the human body. So please don't try that. And just laying out and tanning isn't necessarily going to prevent COVID, but it would kill the individual viruses if they were exposed to the sunlight. So even with that sunlight, it's good, but with concentrated ultraviolet, it would kill the virus. So given that it could do that, imagine what it could do if we didn't have the ozone layer, okay? I mean, it would be good for getting rid of coronavirus, but it would also kill everything else. So ultraviolet light is a little rough. All right, so this is part one. Again, you can pause now if you want to record this all, or I will just post a picture of it underneath, and you can write it down that way. All right, bye.